Hello and welcome to a digital lecture for Salt Lake Community College. This lecture will be the first to cover section 4.2 for Intro to Statistics, considering one sample means with the t-distribution. To start, we will discuss the standard error, which will be used to measure the variability in what will be known shortly as the t-distribution, and has a formula of sigma divided by the square root of little n. Note that the standard deviation, or the population standard deviation, is known to measure the variability in the normal distribution. But this takes that normal distribution and adjusts it or changes it based on the size of the sample, little n. If it is the case that the population standard deviation sigma is unknown, which can happen in many realistic cases, we instead use the sample standard deviation, little s, in place of sigma, resulting in the formula of little s divided by the square root of little n. I mentioned the t-distribution a couple times now, including in the title of this section, so let us define what exactly I'm referring to. The t-distribution is a distribution with a bell shape that looks very similar to a normal distribution, but with tails that are thicker or more variability. The t-distribution will be a very useful tool for us statisticians, as it has a quality known as robustness. Being robust means that it is not overly sensitive to departures from normality, so the t-distribution will work reasonably well because it is robust, as long as there isn't extreme skewness or outliers in the sample data. If we tried to rely on the normal distribution for everything, we would risk minor departures from normality influencing the results heavily. However, in order to even use the t-distribution, we need to ensure that the sampling distribution of x bar, the distribution of sample means, is approximately normal. Our conditions for this are, first, that the data comes from a random sample or a randomized experiment. The second condition is that the sample observations are independent. We can check this by ensuring that little n, the sample size, is less than or equal to 0.05 times capital N, or 5% of the population size. Lastly, our third condition is that the population is normal, or the sample size is above 30. This will be a very important condition in a moment. If these conditions are met, then the sampling distribution of x bar is approximately normal with a mean of mu and a standard error, as we've discussed before, of sigma divided by the square root of little n. Since the t-distribution is robust, the population can be considered normal as long as the sample data do not have extreme skewness or outliers. The standard error may be approximated instead using little s divided by the square root of n. The next page will bring us to a diagram of an important concept, the central limit theorem, which was the third condition listed for the approximate normality of the sampling distribution. The condition that states that the population is normal or the sample size is above 30. We have here a relatively simplistic diagram. We have any shape for the population with a distribution with a mean of mu and a standard deviation of sigma. If the sample size, little n, is greater than or equal to 30, then that means that the sampling distribution will thusly be bell-shaped, and will have a mean, as defined earlier, of mu, and a standard deviation, again defined earlier, as sigma divided by the square root of n. Couple notes. The sampling distribution will be normal if the population is normal, n greater than or equal to 30, or both. Note that we do not need both conditions. One or the other would suffice, but if we have both, then that's also good. Generally, the larger the sample size, the more normal the sampling distribution of x bar becomes, especially for very non-normal original distributions. Overall, what we will see is that as our sample size increases, the distribution itself approximates or becomes more similar to the normal distribution, what we are used to. A consequence of this is that we can use the standard normal table to compute probabilities associated with large enough sample means, even if the population is not normal. This is very useful for us because not everything is going to have a normal distribution. If you have any further questions, be sure to review the example videos or ask your instructor.